What's up, guys? Welcome back to episode 3 of the Simple Transformers series. So I've made some progress. Nick and I took a look at some of the problems I was having, and we managed to, solve a couple mysteries, but then I think there's maybe one or two things that are still kind of confusing me, but let me show you what I've learned since the last episode. So one problem that we had was that with the COLA data set, we tried using the early stopping, and then we tried taking the best checkpoint from the training, the one that did the best on the validation set, and we tried using that on the test set, and it didn't go so well. We got the score we got on the test set was worse than what we were getting on the validation set, and it was worse than what we were getting in the original notebook without simple transformers. So it was kind of confusing and discouraging. Turns out that was largely due to a mistake on our part. The COLA data set actually has 3 data files in it, and there's 2 versions. There's a tokenized and raw. We want the raw. We don't need the tokenized version because BERT does its own tokenization. But there's a in-domain set and an out-of-domain set. So there's in-domain training, and then there's 2 test sets. One that's also in domain, and then one that's out of domain, just meaning that it came from different sources than the in domain data set. So you could almost call it like training sources A and training sources B or something like that. So we were testing in the original notebook and up until now using the out of domain test set. And it is actually expected that you would perform worse on the out-of-domain data than the in-domain data. And in fact, if you go look at the benchmark scores where people have submitted their results on COLA, and they submit both for the in-domain test and the out-of-domain test, and the out-of-domain scores are consistently worse. So so that kind of explains that behavior. Lego ship's coming along nicely here. This is the Rex Celsior from the sequel to the Lego movie. It actually belongs to our middle son, but he kind of lost interest halfway through maybe, so I've sort of picked it up and planning on finishing it. I figure AI and science fiction are kind of go hand in hand, and science fiction and starships kind of go hand in hand. So I figure there's a good chance that you like starships as much as I do. I love Legos, love starships, so it's kind of fun to mix in some of my other creative interests here for a little variety. Maybe I'll kind of show off the build when it's done at the end of this video or end of the series, something like that. So we've been looking at with the COLA benchmark, we've been looking at this approach of using the best checkpoint from training. And in our original notebook that Nick and I wrote on applying BERT to sentence classification on the COLA benchmark, we plotted this learning curve, and it shows that the training loss is going down consistently over the course of training, which is what we'd expect unless something was broken. But then we're also performing validation on this small validation set, and we're seeing the validation loss going up over the course of training. So that means that the model is getting more and more accurate on the data it's being trained on, but it's actually losing some of its generality, and it's starting to perform worse on training on samples that it hasn't seen, that aren't part of its training set. So the idea with the best checkpoint then is that rather than using the model at the very end of the training process, it would probably be better to pick a checkpoint of the model from earlier in the training process where the validation loss was the lowest, because presumably that model has the best ability to generalize. And we did that in episode 1, but it didn't work. It actually performed worse. But we learned, as I just explained, that I was using the wrong test set. I was using out-of-domain test samples instead of the in-domain test samples. So I fixed that. We're going to rerun the experiment. I've also kind of made some other improvements to how I'm using simple transformers and weights and biases. And there's a couple questions we're going to try to tackle here. So question number 1, we want to know does this best model, best checkpoint strategy work? Does it actually improve your results over just using the model at the end of the training run? And then the second question I want to answer, just kind of from my experience playing with this data set, it seems like the scores that I get on this data set vary a lot from run to run, even with the same parameter choices. So due to variation in the random order of the batch selection, the training batches, as well as maybe the random initialization of the classification weights. So I want to see just how much that variance is, because I feel like that might be key to understanding some of the things we're seeing. So we're going to try to answer those two questions. All right, let me take you through the updated experiment code here. So I've preserved the code from the episode 1 notebook. So I'm using the same hyperparameter choices and simple transformers configuration settings. But down in this section, I have made a few changes based on my experiences with the library so far. So one is that I wanted to do more validation tests during the training process. So I had calculated there's 241 steps per epic. So I was doing validation runs every 120 steps, so twice per epic. I'm increasing that to 6 times per epic, so we can hopefully catch that gives us more precision on the validation loss curve, and hopefully we can select a better best checkpoint because we'll have more data points to look at. And then early stopping, I'm essentially churning that off. What I realized is that early stopping is kind of just about saving on training time and training, compute resources. So really, it's not necessary for this best checkpoint strategy, right? We can let training run all the way to the end, and then go back and pick the checkpoint that we want. Early stopping just means that knowing that we're going to do that, ideally you can stop training, stop using the GPU as soon as your validation loss starts going back up. So for now, since the training doesn't take that long, I'm just going to essentially turn off early stopping by setting the patience really high. And then, right. We were running validation between each epic, but that's redundant. My checks are, every 40 steps. So there's one that happens at basically the end of the epic already. So turn that off. And then turning off the printouts, we're going to look at weights and biases to see the results of this training. So we don't need the printouts in the console, or the output cell weren't really helping me that much. So turning those off. All right, yeah, and then I've seen a few user warnings that I don't need to see that over and over again. It's just cluttering the output, so I'm gonna ignore those. And then I think maybe a good practice, if you're kind of running notebooks over and over again and you're using weights and biases, it's easy to end up in a state where technically your previous run is still going, and it won't be officially stopped until either you call a init for a new run or you explicitly call finish. So I call finish explicitly here just in case there's any previously running wandb run, and I want to kind of wrap that up here before moving into the experiment. Cool. All right. There's a few different things to point out here about the new code. Maybe the biggest one is I'm running multiple trials here. I'm going to run this 10 times to see how much the scores vary between each run. And yeah, I've got to set my wandb project name. And then I did figure out how to create or define a custom name for each run. So I'm just going to name my runs trial 0, trial 1, trial 2, and so on. Yeah, and in a different, if I was doing more of a hyperparameter search, I think maybe naming the runs based on the hyperparameter choices might be a better idea. But here it's the same configuration options, same hyperparameters, just run 10 times. So I think trial 0, trial 1 is a good name. And the way you set that is that this is this model args object is the configuration object from Simple Transformers. And it provides this parameter wandb keyword args. And what it lets you do is define a dictionary of additional keyword parameters that you want passed to the call to wandb.init. So whatever function parameters there are to wandb.init, you can set those essentially by leveraging this wandb keyword arguments dictionary. So I'm gonna set the run name in there. That'll get passed down to init, and then on the wandb site, my run will be named trial 0. All right, and then I'm doing the train and test split on each trial because again, I kind of want to see like how much impact does the choice of validation split have on the scores. Okay, yep, and then then we just go into our train and test. Something kind of real quick. So training model.train model is how we train, and then evaluation model.eval model is how we test. Something kind of that I had some trouble with Simple Transformers is when you call train model, it starts a new run, calls init, and then when you call eval model, it also calls init, and so that actually tells weights and biases to end the previous run and start a new one with a different name, which is not what I want, right? I want my test scores to be in the same run with the training figures. So I needed to find a workaround for that. It was kind of tricky, but I did figure it out. Essentially, we can use that keyword arguments object again, and if you pass it, there's every weights and biases run has a unique ID. It's separate from the name. The name doesn't have to be unique. The ID is unique, and you can look up the ID of your current run by accessing the wandb class and then looking at this property here, wandb.run.id. So we can retrieve our current run ID, and then we can add it to the keyword arguments dictionary. And that way, the Simple Transformers library is going to pass that ID into the init call inside of eval model. And that'll tell wandb to append whatever data gets recorded during the evaluation, add that data to my existing run instead of creating a new one. So that's the workaround there. And all right, so for the test, I'm running 4 tests for each of these trials. The first 2, I'm using what I'm calling like the ending model. So this is the version of the model that we get after completing all 4 epochs of training. So this is the model that we think is overfitting basically the training data. And I'm going to test it both on the validation set and the test set. Maybe just to see if there's any clear pattern between these two. Like is the validation score always higher than the test score or something like that? And then I want to compare those to the best model, right? Where we the model with the lowest validation score. And Simple Transformers kind of handles that for us during training. So it keeps track of the best validation score, and that model gets saved as a checkpoint. There's a folder outputs/best model, and that contains our best model checkpoint. So we can load that best version back in with this call, and then again I do need to in order to append my these test scores to the existing run, I again need to set that ID parameter. So I'm doing that. And then test against the validation set and the test set again. And then that will let us compare the test score with the best from the best model versus the ending model. So let's take a look at that, at the results of this on weights and biases. Apparently, I was actually really close to finishing this thing and didn't realize it. I just had a lot of pieces left on my tray, so I figured there was more to go, but really I just had to build the little blaster piece up front here. So yeah, in addition to being a ship, this thing's also a giant gun. It's got like a pistol grip in the back here that you can wrap your hand around, and then a trigger in there you can't see, but I can shoot it. Yeah. Am I getting you? Awesome. All right, back to it here. Here's the weights and biases dashboard for that experiment. And even with that out-of-domain test sample issue resolved, I've still been having a tough time explaining some of the results that I'm seeing. I think I've just had a breakthrough on this though. So let me show you what I've got and what I'm thinking. So this first plot here is the validation loss over the course of training. And each of the different lines corresponds to each of the 10 different trials that we ran. And the blue line up here is trial 0. That's the first trial. And it shows the kind of overfitting behavior that we've been seeing in all the versions of the notebook that we've played with here, where the eval loss goes down maybe initially, but then it starts to go back up. And then all 9 other trials that we ran have this kind of like smooth downward curve, right? Which doesn't show any overfitting, and I don't know how to explain that. So I've struggled a bit with the logging behavior in the simple transformers library. So I think I was kind of quick to blame the library. I figured maybe it was logging the validation loss incorrectly somehow. Maybe it was logging a different variable, not the validation loss. So I tried digging into the code, but I couldn't find any evidence of that. Couldn't find any bugs that would explain this behavior. But then I did finally come across a different piece of evidence that I think gives a strong clue as to what's probably happening here. So this second plot that I've pulled out here is the Matthews correlation coefficient, basically our benchmark score on the validation set after the training is complete. And again, we've got the 10 different trials here. Trial 0 is the blue bar at the bottom, and it got an MCC of 0.5368 on the validation set. And that's a very reasonable score. That's pretty consistent with other scores that we've seen on this benchmark in our various notebooks. But then all of the subsequent trials have these really high scores, 0.921, 0.8962, yeah, much higher than is reasonable. So what would cause the model to score so highly on the validation set? I think it's got to be that somehow the model has been able to train on those validation samples. It's seen them somehow, and it's been able to fit itself to them so that it's scoring really well on them. Which shouldn't be possible, right? Because I'm splitting the data set into a training set and a validation set, and very specifically do not include the validation samples in the training data. Here's how I think that's happening. So back to our code for the experiment. We've got our 10 trials here in our for loop, and we are creating a new training and validation split each time for each trial. This is using the scikit-learn train test split function. And then this step here, my expectation is that this step will set up the BERT model and load it with the original pre-trained weights from Google, right? The BERT base uncased weights. But what I think is happening is that on the second trial, when we get to this step, it's not actually starting fresh. It's not reloading those original pre-trained weights. It's continuing with it's keeping the weights from the previous trial. And some of the samples that are in our new validation set, because it's randomly selected, it makes sense that some or most of the samples in our current validation set were in the training set of the previous trial. So essentially, because we're continuing the fine-tuning rather than starting over, the model has actually seen some of those validation examples, and that's why it's scoring so highly on the validation set. So I think that should be a relatively straightforward issue to debug. I can kind of go into this this initialization function and figure out what's going on. So I will dig into that, and then hopefully we'll get some results out of this experiment that we can actually trust and we can actually analyze.